Good day and welcome back to the sixth and final part of our discussion on substitution. So as indicated at the end of the previous video, this is a point where I'd be turning the floor over to you as students if we were meeting in person. And hopefully you've taken some time to work through these two examples before viewing this video. And if not, this is a perfect opportunity to pause the video and do a little bit of practice. Remember, we get out of this experience what we put into it. And oftentimes the best way to learn is to see a few examples and then practice some on your own and even be forced to struggle a bit to complete those examples. So the quick reminder, when we are using a substitution on a definite integral, our approach is going to be procedurally the same. We choose u somehow to be an inside function, possibly the largest possible inside function. So in this case, u is g of x. Du would be g prime x dx. So we start off with this definite integral, all in terms of that variable x, even the limits of integration. And the goal is to express it in terms of an equivalent definite integral, only involving the variable u. And the idea is it should be simpler for us to evaluate. But that means we need to also switch our limits of integration so that they only involve u. And the substitution is what allows us to do that. If you know the lower limit of integration corresponds to x equals a, in terms of u, that becomes g of a. And for the upper limit of integration, when x is b, u is g of b. Once you've rewritten in terms of this equivalent definite integral involving the variable u, you simply evaluate, and that is your solution. With definite integrals, no resubstitution is required. So with this intuition in mind, in the first example, there is no obvious way to relate this back to any of our common indefinite integral or anti-differentiation formulas, so the only other possible choice is a substitution. And there's several possibilities you could try for u, maybe something to do with, say, x squared in the bottom. But the thing that really sticks out to me is this 1 over x inside the cosine. That's troublesome in comparison to our known or common formulas. So let's try u equals 1 over x. And note, just for convenient, 1 over x is x to the minus 1. So du would be the derivative of 1 over x, so minus x to the minus 2 dx. And for convenience, let's write x to the minus 2 as 1 over x squared, and then we'll put the minus sign with the du. The reason I would suggest that is if we rewrite this integrand ever so slightly, and you don't have to do this, but I just think it makes it easier to see where everything's going. We have cosine of 1 over x times 1 over x squared dx. U is 1 over x. 1 over x squared dx is minus du. So once again, getting the integral solely in terms of u follows using our previous procedure. The part that requires an extra step is taking care of those limits of integration. But it's just a computation we can do to the side. The lower limit of integration is x equals 2 over pi. The upper limit of integration is 4 over pi. Our substitution is u equals 1 over x. So if x is 2 over pi, dividing by a fraction is multiplying by its reciprocal. Similarly, if x is 4 over pi, u is equal to pi over 4. So we are now integrating from pi over 2 to pi over 4. And just like we did previously, I'm going to note, we can take care of this negative sign by switching around our limits of integration. And the only reason I'm going to do this here is because the lower limit is larger than the upper limit. If that was not the case, I would probably just leave it in its current form to simply save myself a step of writing. So this would be the definite integral from pi over 4 to pi over 2 cosine of u. And note I've ran out of space, so I'm just going to go up to a new column to begin work. An antiderivative of cosine is sine. And by the fundamental theorem of calculus, we evaluate this from pi over 4 to pi over 2. That is, we replace each u with a pi over 2, minus sine, replace it with pi over 4. And as these are trig functions with common angles, we most definitely need to take this one step further. Sine of pi over 2 is 1. Sine of pi over 4 is 1 over root 2. And once again, let's go ahead and apply this same technique to the remaining example. In order to evaluate this integral, note we don't have any real hope of simplifying this and using our previous techniques. But what we can see is this x plus 1 being cubed in the bottom, so maybe a substitution would work. And in fact, if a substitution is going to work, I think u equals x plus 1 is the only reasonable choice that we could hope for. So that would make du dx. So x plus 1 is u, dx is du. That does leave this troublesome x left over. But remember, whenever that occurs, you simply go back to your substitution and solve for x. The x will become a u minus 1. And with that observation, we've taken care of our integrand. It will be u minus 1 over u cubed du. And from an integration perspective, this is something we can certainly handle by breaking it up into two separate fractions. But before we get carried away, remember we need to change our limits of integration. Lower limit is x equals 0. Upper limit is x equals 2. For that lower limit, when x is 0, the corresponding u value would be 0 plus 1, which is 1. And for the upper limit, when x is 2, u is 2 plus 1, which is 3. We now have an equivalent definite integral written solely in terms of that variable u. Once we evaluate and get our solution, a numeric value, we will be done. No resubstitution is necessary with definite integrals. So algebraically rewriting this integrand, u over u cubed minus 1 over u cubed. U over u cubed is 1 over u squared, or u to the minus 2, and 1 over u cubed is u to the minus 3. And individually, we can take care of each of these terms. Minus 2 plus 1 is minus 1. So we would have minus u to the minus 1. And then we're subtracting away. And note with n equals minus 3, this power of the second term involving u, minus 3 plus 1 is minus 2. So we would have 1 over minus 2. Now I'm going to go ahead and make this a plus 2, because minus a minus. U to the minus 2 from 3 to 1. And for convenience, I'm going to go ahead and rewrite this so that our exponents are positive. And then we simply substitute in a 3, put a minus sign, substitute in a 1. And as usual, we most definitely could do a step of 2 of arithmetic and get this down to a single fraction. But I'm going to leave it precisely in this form. You are more than welcome to do so as well. And with that, this completes our discussion of substitution. And in fact, it completes the entire chapter related to the definite integral all the way through substitution. What remains for us this semester is to investigate applications of the definite integral. And when it comes to applications of definite integrals, it will always involve setting up a definite integral that we in turn solve. So solving one of these definite integrals is going to become a smaller part of a larger problem. So as I've kind of foreshadowed previously, this is a great opportunity to practice suggested problems. We want to be as efficient as possible when it comes to evaluating these definite integrals. So practice suggested problems, reach out to me when you have questions. Stay tuned and take care.